We're not going to do two lectures on how we do viewing with WebGL. It's going to be very dependent on using functions that are in the MVJS package, but they are going to, as we see, mimic the functions that were in the old fixed function pipeline. Now I'm going to divide this up into two parts. This lecture will be about how do we position the camera where we want, how do we locate it, and how do we point it at something in our scene. The next lecture will deal with now how do we equivalently adjust the lens on that camera, which will control how much of that world we see at the direction that the camera is pointing in. And they'll define a model view matrix for the positioning and a perspective matrix that'll deal with how much we see. Okay, so I'm also at some point, actually, which will be next week, talking about the mathematics of projection and how we, what do these matrices actually look like. But by using these viewing functions in MVJS, we'll be able to use them and specify them in terms of parameters that make sense in the application without having to go in great detail through the mathematics, although we'll see in these two lectures just a little of the mathematics for the simple cases. And I'll also look briefly at some other ways of getting an application programming interface to how we do the viewing. Okay, so going back to the original days of OpenGL, when we had just the fixed function pipeline, it defined a sequence of frames that were built into the system, namely that you started with the model frame and then you took models into an object frame. Often they were the same. Then you went from the object frame to what the camera saw, that was camera coordinates. Then you went into clip coordinates, which would sort of normalize you so that you could clip against the standard box. Then you went into what were called normalized device coordinates, and finally you went out off into window or screen coordinates, which were the appropriate system for the physical device at the end. And that defined in it a number of transformations. The ones that were closest to the application were the transformations that went from the model to the object to the camera, just for the positioning, and they were all put into a single transformation called the model view transformation. And so what you had were functions in the fixed function pipeline that would just say set the model view matrix to certain things, certain values, or manipulate the model view matrix. The projection matrix was the one that carried you from camera coordinates to clip coordinates, and they would deal with what you could see and not see, and that was specified within a projection transformation, and you could either build it yourself or there were some functions that we'll mimic later, Frustum and Perspective, that will do it for you for the standard transformation. So that was all built in. The problem, as we saw in our last lecture, was that all of this happened before the shaders. It was done in the CPU so that when deprecation came along, these functions didn't make as much sense as they did previously. So after deprecation, you basically had nothing. You wiped out all of these functions, so there were no more transformation functions in there at all. But on the other hand, you had this pipeline with programmable shaders in it. The one that's most important for this discussion is the vertex shader, because we're going from vertex to vertex to build up our objects. Internally, there were some frames that are known, because as we've seen in our simple examples we've done, we've been able to work in clip coordinates because the rasterizer has a fixed box that it does clipping on. That's the box from the principal diagonal is -1, -1, -1 to 1, 1, 1. And the output of that is normalized device coordinates that then go off to screen or window coordinates. So those frames at sort of the end of the pipeline still exist, but all of the stuff in sort of the user space, the application space, the camera coordinates, object coordinates, model coordinates are totally up to you, and as And to get between them, you have to define the transformations. Now, we've gone through transformations, so you should, at least in principle, understand how you can combine them to get a desired transformation. But what we've done with MV.js is say, let's reconstruct those functions that used to be in the fixed function pipeline. We did that with rotation and translation and scaling. We're going to do the same thing so that we can make the equivalent calls to get a model view matrix and a projection matrix. But the big difference is that rather than those matrices actually doing something within the fixed function pipeline, they're simply going to produce matrices, and you can decide what you want to do with those matrices. What you'll see is that the simplest situation and will be that we form those matrices using functions that look like the fixed function pipeline functions, but we'll take those matrices and actually have the operations carried out in the shader. So we'll use we'll make them into uniform variables and transfer them over. Okay, and we'll see that as we go along. So viewing is generally broken up into 2 or 3 parts. The first part is, as we've been talking about, is positioning the camera. That's setting a model view matrix. Setting the lens is the projection matrix, and setting the clipping sets a view volume. In some ways, these 2 operations are really both implicitly within the projection matrix, because when you select the lens for the camera, you really are determining how much you see, because things, if you have a very long telephoto lens on a camera, you can't see things except in this very narrow range coming out from the camera. So in a sense, you're defining some clipping. The main difference here when we say, oh, well, we're setting the clipping explicitly, is something we discussed briefly when we introduced the synthetic camera model. Basically, that when you do clipping and viewing with a synthetic camera, you also clip in the front and the back. We don't see out to infinity, and we only see things that are a certain minimal distance out. So both of these are embedded in the projection functions that we're going to talk about. But this lecture is about the model view matrix. So let's talk about it. So initially, if we think in terms of these frames, now again, these frames don't have to be there. You can write an application with none of this, and in fact, we've been doing that by starting in clip coordinates. With the more general case, you say, I'm going to use a model view matrix. I'm going to start off in model or object coordinates, and I am going to get me a model view matrix that carries me from the object coordinates out to clip coordinates. And that fits in now with the WebGL camera, which by default is located at the origin in its own system, and it points in the negative z direction. Okay, and that clip coordinates, this is what we're seeing over here, is that cube with sides of length 2 going from -1, -1, -1 to 1, 1, 1. So in other words, what's happening here is if you say you're going to use a model view matrix and a projection matrix, you can argue that the default model view matrix and the default projection matrix are just identity matrices, and assume that the camera, then if you use the defaults, is this camera pointing in the negative z direction. So here's just a little picture of that. Saying that, so then things that are inside that camera will get projected into this plane z equals 0 and be potentially visible. They may be hidden by something else and removed by hidden surface removal, but if they're not, then they're visible, and polygons that are outside of this area are clipped out. So that's the process in terms of clip coordinates, and by having used clip coordinates previously, this was our starting point. But now we're going to do things a little bit differently. I want to put the camera somewhere else to start with, and then in the next lecture I want to be able to change the lens. Okay, so first let's look at moving the camera, and we saw one example of that lecture or two ago where we said, look, this camera is pointing in the negative z direction. What if we have objects in both the positive z area and in the negative z area, and I want to see them all, then I have to do one or two things: move the objects and move the camera. Now, in both of these views are equivalent in the sense that you have two frames, and what's important here, the model frame or the object frame and the camera frame, and what's important is the relationship between the two, not that you're moving one or you're moving the other. And that's so every transformation sort of depends on how you want to look at it. Are you moving A away from B, or are you moving B away from A? My advice is don't confuse yourselves. Pick one of those views and try and stick to it, because otherwise you start moving things in the wrong direction. But in either case, all I want to do is separate the camera from these objects on both sides of the z=0 plane. I want to do a translation, and if I do pick a d greater than 0, if I use a translation with minus d, that will move one. Well, let's do it this way. Let me argue this. I used to argue the other way and say that the objects are fixed because that's the physical view, and the camera moves. But I'm starting to think now it's better to think in terms of OpenGL, WebGL terms, that, hey, this camera is fixed and I put things where the camera can see them, so I'm going to move my objects this distance minus d away from the camera in order to see them. So, pick the way view, but in either case, this is what you're doing. In the end, after these frames are the same, and after we've applied this transformation, the two frames are separated, and now our camera can see all the objects on both sides of the plane z=0. Now let's look at slightly more complex example where what if I want to see these objects from the other side? Now I want to move the camera away, and I also want to do a rotation. And you can do this a couple of ways. Think in terms of the model view matrix, which often is the current transformation matrix we talked about earlier, and say, okay, what are we going to do? Well, I can do it this way. I can notice that the one on the right is the one that's going to be applied first. So what if I first rotate the camera and then move it out here? Okay, so I'm going to do a rotation followed by a translation. Now, this is a little tricky in a way, because if I did move the camera over here first and then I did a rotation, I could wind up in exactly the same place. So a rotation followed by a translation followed by a rotation is a possibility. You'll notice if you do it that way, the parameters turn out to be slightly different, but still, this is what we do. We need the combination of a rotation and the translation. Now, but the point I really want to make here is that we really have multiple ways of doing this. And if I really want to do something like create an isometric, what I'm going to do is put the camera, sort of, if I drew a line coming out here symmetrically, coming out towards me, from the origin, I would want to place the camera there pointing at the origin. Now, you can do as a little exercise, what sequence of rotations and translations do you need to do that? That's the problem we're trying to get to. But first, let's look at this example and say, okay, so here's the kind of code you can have in MVJS. What I could do is I could make a translation matrix. See, this is what we've done. We've put these functions in there, and again, the difference between this and the old fixed function pipeline, these simply form objects that you can use. They don't do anything to your vertices or graphics unless you make them do it. So here, this forms a translation matrix. The rotate y function returns a rotation matrix of 90 degrees about the y-axis. There's a rotate x, a rotate y, and a rotate z, and then I could use the mult function to multiply them together, and this would be my model view matrix. You can also, it's done in a way, and this is a JavaScript feature to let you do this, you can chain these together. So I can simply write one line that says this model view matrix is the product of a translation and a rotation, and I don't need these intermediate matrices. Now, if I gave you this harder problem and said, Well, what if, let me come back here for a second and say, well, what if I wanted an isometric? Well, now I've got to get the camera up a bit, up a bunch. I have to, so this rotated about Y, but now I'm going to have to rotate about X, and how am I going to get it pointed the way I want? You can do that, and I think there's a, yeah, I know there is. In the notes, there's a derivation of what these angles have to be in order to get an isometric, and they're not going to be what you expect. You say, oh, symmetry, I'm going to go 45 degrees here and 45 degrees up. That's not going to work, and you'll see why in that discussion. But a more general problem is this is not a particularly good interface. Say, how do I want to specify where a camera is, and specifying it as a sequence of rotations and translations in some way about different axes is not a very intuitive way to look at what I'm trying to do. What I really would rather do is have something like this, is a function, we're going to derive a function called look at, but the importance of it is saying, I look at something. That's what I do if I'm the viewer here and I'm the camera. There's a point I'm looking at, and my camera, I'm looking at this point, and the camera is located, it starts off locating in a certain place, and we call that the eye point. Okay, so there's a line from the eye point to the at point, which is determining the direction of that camera. That's a very simple interface because the software can figure out all the required rotations and translations to give me that. And the only thing that's missing here, this doesn't totally fix the orientation of the camera. See, the camera is sort of, you get where it is by saying, give me the eye point. You get the direction, or, this is actually a perpendicular from the lens that's going from the center of projection, the eye point, to the at point. But there's a degree of freedom missing because I could rotate the camera about that vector, and everything is unchanged. I still have the same at point, the same eye point, and I have this arbitrary rotation. So you need a third parameter, and a third parameter is the up direction for the camera. Which way is up? One way to think of this is you're in an airplane and you're pointed in some way, and that's, you're the eye in the airplane, you're the pilot, say, and you're looking at something, and if this plane is spinning, it's crashing and it's spinning, imagine the image you're going to get. It's spinning around, but it's always pointing at the same point. But once I fix that at point, now the spinning stops. Now, mathematically, this again is in the notes, it's easier to just say, give me the sort of the direction up, but if this is in an odd orientation, that could be a little difficult. See, look at it this way. If I look at it in terms of the back of the camera, this vector here, going from the eye point to that, is a perpendicular to the back of the camera. Here's the up direction in the camera. But the problem is I may not be able to represent that easily in whatever frame I'm working in. If I give you an up direction as an X, Y, and Z, then what we're going to argue is that the up direction that I'm actually going to use is the projection of this vector from up X, up Y, up Z at the eye point back onto the film plane, so that will give me the up direction from that. And that's built into the function that we're going to give you. So it allows me now to easily specify it. In a simple example, you would say the up direction is the Y direction. But if this camera now is tipped because it's pointing towards the at direction, it may not be so clear. So the look at function takes care of all of that for you. You just give it the three vector, the point, the eye point, the up direction, and the at point, and that's all it needs to do that. In the old OpenGL before deprecation, there was a function called GLU look at in the GLU library. It was in the utility library because you were able to, in principle, construct that from simpler functions that were in the OpenGL library, but it was sort of helpful to have it. What we did is just simply put it into mv.js, and it's called look at, and you use it just as in the diagram, for example, if you want an isometric of a cube, rather than try and figure out any particular angles to get things right, I'm just going to say, look, I have my object. My object is centered at the origin, so that's the point, the at point. I want to look right at it. And I'm going to be along that line that's symmetrically coming out of the origin. So I can say give the I point as 1, 1, 1. 2, 2, 2 would do exactly the same thing here, except for the clipping issue we'll talk about in the next lecture. And let the up direction be my standard up direction, where y is up, 0, 1, 0. This would be give you an isometric view by just now setting your model view matrix to be look at of I, at, and up. That's it. And this is obviously far simpler than trying to figure out what all of these angles and that all these rotation matrices need be. Okay, so that's the standard way we're going to do it. And certainly you can, and we'll see in the next lecture, your ability to say, well, what if the eye is moving? What if the camera is panning to the left and the right? Well, fine. Just in your render function, keep changing this in any way you like, and then compute a new model view matrix with the changed eye position, and then send that over to the shader as a uniform variable. And that's what we'll see in the next lecture. Just finally to mention, there are a few other ways to do this. You can actually reduce any of these to this look at kind of model. I mean, most people who do graphics really like the look at idea because it's very natural for a viewer. But there are others that come back from other systems. Previous system, FIGS, which we've mentioned before, and GKS used a system where you had a view reference point and a view plane normal and an up direction too. It turns out that given the view plane normal and the reference point, you can get the at point and the I point, or go backwards from the I point and the at point to the view reference direction in a view plane normal. So this is equivalent. If you're in the aircraft industry or any aerospace industry, then the more natural thing is to talk about yaw, pitch, and roll. That yaw is sort of the sideways motion of the airplane if you're sitting there left and right. Pitch is the up and down, and roll corresponds to the up direction. So again, it's pretty close to what we had. Elevation, azimuth, and twist is if you're pointing at any of you who work with telescopes and you say, well, how do you decide? How do you give the position of a star? You give it at a given time. You say, well, how high is it above the ground? That's its elevation. The azimuth is pointing now your telescope relative to some fixed orientation, north or south. How do you rotate it? And we've seen that before. That's a 2-angle specification to get the direction to point to a star. But now you get into the same issue. You can now twist your telescope around or spin your telescope around that line pointing to the star. So if you want to fix that, that's called the angle of twist in there. So elevation, azimuth, twist is an equivalent way to do that. And certainly you can go back and talk about, as we did a couple of lectures ago, talk about direction angles and Euler angles and all of these things. And so you can convert between any of these representations. But I think you're going to find that look at is probably the most convenient for the applications you're going to be doing. Okay, so the next lecture now, we're going to turn to actually how do we do the actual projection, an orthogonal projection, a perspective projection. And now we're going to get matrices that have somewhat different properties. They're not going to be affine matrices. They're going to be projection matrices, which will still preserve lines, but they're not going to preserve the parallelism of parallel lines.